Good day, everyone. Today we will discuss about digital buck converter with peak current mode control. So, for a better understanding of this content, you may refer to the previous videos, buck with analog peak current mode control for the peak current mode control theory, and buck digital voltage mode control for the specifics of the digital implementation. So let's start. Digital buck converter with peak current mode control. As we can see here in the picture, we have the power stage of the buck converter, as we know already, and we have on one hand the output voltage, which is scaled down by a resistor divider. So we have this gain of the resistor divider, and then we have the MCU. Inside the MCU, we have the analog to digital converter that takes the scaled down output voltage and converts it into the digital domain. As soon as we have it into the digital domain, we have here also the digital reference, and the difference of the two is just the error that is applied to digital compensator, which is this HC of Z. Then it goes to a saturation block. We have the compensating gain, and then we have the DAC, digital to analog converter. So more or less the output of the digital compensator, we are translating it back into an analog signal, and we are then subtracted the external slope or the slope compensation, and in the end the difference of the two gives the reference for the peak current. The inductor current, or at least the ramp up or the positive slope of the inductor current, is sensed here, and we have a gain called sense resistor, or RI. We will see it later on. That goes to the other input of the comparator. So as long as, or as soon as the sensed current becomes equal or just slightly higher than the reference current, then the output of the comparator will change its state and will reset the flip-flop. So the basic operation of this peak current mode control can still be linked to a SR flip-flop, but the oscillator and the flip-flop, if you want, are just inside the PWM peripheral of the MCU. So at the output, finally we get the control signal for our MOSFET here. Okay, we talk about the compensating gain. So because we basically want to control the output voltage, that means we need to cancel the effect of the resistor divider gain. We also need to cancel the gain of the ADC, and we also need to cancel the gain of the digital to analog converter. Therefore, this compensating gain has this expression here. Yeah, and of course, gain of the ADC is just 2 at the power of number of ADC bits minus 1 over ADC reference, and the gain of the DAC is the DAC reference over 2 at the power of number of DAC minus 1. Okay. Then we know already from digital buck converter with voltage mode control that we need to target a smaller cutoff frequency, something like switching frequency over 20, mainly because we have a phase erosion mechanism. So every delay in the sampling or ADC sampling of the output voltage and processing inside the digital domain. So every delay will come with a decrease in the phase. So for our analog, for our digital peak current mode control, we will target the same 5 kilohertz cutoff frequency, and because we are going to have in the end the same transients at the output, that means we can use the same power stage as we calculated for digital buck converter with voltage mode control case. So the inductance will have the same value, and especially the output capacitance will we will use the same. Okay, so as we did it previously, to calculate the compensator, we will do it first in analog domain, and then we will translate it into the digital domain by calculating the coefficients of the linear difference equation. So first, what we need to know is the plant transfer function, and we want to extract the gain and phase at the desired cutoff frequency from the plant Bode plot. Okay, so for this, I prepared a simulation making use of the three-terminal PWM model. So we have an averaging model, and I implement all the necessary equations for the peak current mode control implementation. We know from our previous examples that the peak current for an input voltage of 12 volt and an output voltage of 5 amps and an output current of 2 amps, and for the inductor value we calculated, so this 36.46, we know that the peak current is 2.4 amps. So, and because now we have digital implementation, but in the end we will have usually an analog comparator, which is normally included in the DSP or the microcontroller we are going to use. And we know that the MCU or DSP is normally supplied by 3.3 or 5 volt. Then we will target a sense resistor, a current sense resistor of 1 ohm. So this will give us the let's say a good how to say it, not sensitivity, but a good resolution, yeah, to say like this. So yeah, of course, one can use a much smaller current sense resistor. Let's say we want to compare only maximum up to 1 volt, but if we take 1 ohm for 2.4 volt, we will have 2.4 volt plus something from the external slope. So we will probably be closer to 2.7 or something. So that means we will still have some margin for the overcurrent if we want to implement this with a second comparator to be able to react in yeah, in special cases like short circuit on the output or other yeah, events. Okay, so we will calculate, or the equations that are used here are calculating the external slope for QP of equal to 1. Okay, running the simulation, we see that at 5 kilohertz we have about minus 20.8 dBs here, and we have a phase at that point of about minus 92.5. So we will use those values actually to calculate first the compensator in as I said, in analog design, because the plant transfer function looks like first order low pass filter, or resembles that at least. We know that we can then use the type 2 compensator to stabilize, I mean, for the voltage loop of this converter. Of course, we know the transfer function of this type 2 compensator. And then, as we did it for the buck voltage mode digital buck with voltage mode control, we will apply the bilinear transform, and we will replace the Laplace operator with a Tustin approximation, and then we will get this discrete h of z transfer function in this form, and then the linear equation, difference equation, will be of this form, where y of n is actually the current output, the y of n minus 1 is the previous output, previous output. This is the current input, and previous input. In output and input, referring here to the digital HC of Z, digital compensator. Okay, and then we have the equations here for the coefficients. And what we will do next, we will actually calculate this. So we will make use of a very simple Python script to get those values, and then we will simply copy and paste them in our C++ file, where we will have the emulated the microcontroller, let's say like this. So we have the sampling period. We will say that we will sample once at every or in every switching period. That means sampling period is 10 microseconds. We of course we will run at 100 kilohertz. And then we want to have 5 kilohertz cutoff frequency, a phase margin of 50 degrees, but taking the worst case scenario with phase erosion, we saw we have like, how much it was, like 9 degrees. It was from the sampling and reconstruction process, and if we have complete period time delay, then we have additional 18 degrees, so in total about 27 degrees phase erosion. So that's the reason why in analog domain we will target for 77 degrees, and then we will expect in digital domain to get something around 50 degrees in the end. Okay, then here are the values we already extracted from the plant Bode plot. And here are the equations based on the k-factor method. So this is the needed phase boost. We calculate the k-factor and the gain needed at 5 kilohertz. And then we have, this is the position of the pole at the origin. So it's simply this expression here, cutoff frequency times the gain over the k. And then the position of the zero and the pole are the geometric mean, around the cutoff frequency. Okay, and then we just calculate the coefficients. Here you see the output of the running the script. The output we get it here. So we have close to 80 degrees phase boost. K is like 10.9, and we have about 11 dBs gain at 5 kilohertz we need to introduce. Those are the position of the poles and zero, and those are the values of the coefficients. Okay, then I set up a new simulation, and we have here a block which is defined as a DLL. This X1 called digital peak current mode control. This is how I name it. We have ADC pin. So here is where we are sampling or reading the output voltage. We have another analog input pin where we have the reference for the ADC. We will use the same reference also for the digital to analog converter. We have this sense voltage input pin, also an analog one. So Here we will actually have a voltage that represents the, in this case, the current to the switch. And we have the two outputs, the PWM high and PWM low, for the switches. Okay, then this R6 and B1 are emulating a current transformer with a turns ratio 1 to 100. And then we are by R4, we are terminating, this is a terminating resistor. We are terminating over 100 ohms. So actually the total gain is 1. So the equivalent sense resistor we have here is 1 ohm as we intended to have. Of course, R5C3 are a small low pass filter. The same C2 is also realizing a small filter for the sensed output voltage. Okay, then we have some input parameters for our DLL block. So we have the switching frequency, the maximum duty cycle sampling frequency, ADC delay, which is the delay from the beginning of the switching period until the ADC is triggered. The ADC conv is the time needed for the ADC to convert the sampled data into an analog, into a digital number. Then we have the number of bits for the ADC and number of bits for the DAC. We have the soft start time. We have the peak-to-peak amplitude of the external slope. We have the desired output voltage, the gain of the resistor divider, and here delay T del 2P to Z is actually delay time from the beginning of a period until the 2P to Z function is executed, and T run 2P to Z is actually the execution time of the function or the linear difference equation. And last input parameter is the dead time. So dead time would be the dead time between PWM high and PWM low. Okay, this is how the C++ file looks like. We have actually a definition of the pins. We have here the parameters, the coefficients actually for the linear difference equation. We have a structure here that we will use it. And here the definition of the type data, and if we have input and input parameter or output, so the type of the data, and yeah. And here, starting here, we will have our code. So we will have a clock generator. Remember what I said, the oscillator would be part of the PWM module or peripheral inside the MCU. So we emulate this by the clock generator. Then we will have a signal ADC trig generator. So on the positive edge or rising edge of this signal, we will trigger the ADC, and on the falling edge, the ADC conversion will be available. And in a similar manner, we have this run 2P2Z generator for the execution of the linear difference equation. We have then the ADC sample and conversion, and at this point we make the new ADC conversion result available. Then we have the soft start ramp implemented. We are then calculating the reference in digital. This is the external ramp, and we are calculating the error that will be the input for the digital compensator. Then we have here, we are calculating the compensating gain, yeah, with the formula presented earlier. And then we run the linear difference equation. And I decided to actually include on the B coefficients or to multiply the B coefficients by this compensating gain, GK. So this is one possibility. Normally it is done like this in a real software implementation because you don't have to do the multiplication inside the ISR, so you just save time. Yeah. Then we have the saturation block, and of course we need to do this to propagate the values. Then yeah, I call it the SR ledge, but it's not really an SR ledge. We have actually the outputs. Here we are calculating the reference, yeah, as being the output of the digital compensator, which is already saturated, yeah, let's say like this. And then we multiply here with the gain of the DAC, and we are generating PWM signals. Okay, and we have here two test points. So those are for development purposes. You can actually output any value you want here, just to check if a specific block is operating as expected. Okay, and this is the last part of the C++ file, where yeah, actually it looks for a change in the PWM, and then we increase the if the case the time step, so that we have a sharp transition on the signals, and in the end we are freeing the memory. Okay, good. Then running the simulation, we get like 4.97 or close to 97, so it's very close to 5 kilohertz cutoff frequency, and we get like 54.7 degrees. This is a bit higher than expected. So I consider that maybe there is a difference in the plant transfer function on the transient analysis compared to the averaged model one. So for that reason, I looked again on this on the plant transfer function, and indeed, if for the gain there is not a difference, but for the phase there are there is a small difference. And then I introduce the new values in my Python script, get the new values for the coefficients, and run the simulation again. Yeah, and this time I get like 4.95 the cutoff frequency, and 49.3. This is closer to what I was expecting to see. Okay, we don't have actually 50 degrees. There is a small deviation, especially this capacitors were not actually considered in the analysis. Yeah. So in the end, if I remove or not populate, let's say, those two capacitors and run the simulation again, I get the same cutoff frequency, 4.95, and this time 50.2 degrees, like phase margin, which is really much closer to the expected result. Okay, as we saw again in buck converter with digital voltage mode control, delaying the moment when we trigger the ADC for sampling by 4 microseconds, we expect a phase in boost of 7.2 degrees. So that means from 50 degrees, we'll expect to have like 57 or close to this value. And indeed, the simulation result reveals that, yeah, we have like 5 kilohertz now, the cutoff frequency, and we have 57 degrees. So in the end, the theory is confirmed. Good. Then it was time to look for the dynamic behavior. So I imposed a step load on the output from 0 amps because we have synchronous rectification and we can tolerate 0 amps at the output. So from 0 amps to 2 amps and back, and we have a DIDT of 1 amp per microsecond. And as you can see here in dark green is actually the current. In bright green, we have the inductor current. And here in blue, we have actually the output voltage. You can see the voltage dip or the undershoot and overshoot are around 200 millivolts. So the voltage drops from 5 to 4.8 and then goes up from 5 to 5.2 volts. And those are acceptable limits. We have a 250 millivolt maximum voltage deviation at the step load, so we are okay from this perspective. Here is the full extent of the simulation time, and we saw that the overshoot at startup is actually smaller than the overshoot we have at low transient. So that means the 2 milliseconds we imposed in the digital controller is enough. Okay, good. Then that's it with the digital buck converter with peak current mode control. Thank you for your attention.